Doctor, I think you are muted.
Yes, Assalamu alaikum warahmatullah. Can you guys hear me now?
Walaikum salam wa rahmatullahi wa barakatuh. Yes, we can.
Okay, gentlemen, I was trying to write the summary of chapter 3, and let me write it, and then I will see if you have any question from this summary. Okay, this is what we have discussed in this chapter so far. Apart from the general case of random variable, this is what we have discussed in this chapter. We have discussed in this chapter so far that if your interest is in number of successes out of n trials, you perform an experiment n times and you're interested in number of successes, then you get to see how are you picking, how are you selecting. If you are selecting with replacement without any question, your four properties of binomial distribution will be satisfied and you will directly use this binomial distribution. That's number one. Now, the second thing is when you are picking without replacement, or there is no statement about with or without replacement, obviously you will assume it without replacement case, then you get to see the size of your population. If the size of your population is infinite or not mentioned in the question, that will also be assumed as infinite size. In that case also your x will be binomially distributed. But for the third case, where you clearly see the size of the population and you clearly see that it's written without replacement or it's not mentioned about with or without replacement, then your x, which is the number of successes, that will follow a hypergeometric distribution. We covered hypergeometric distribution in the last class. Hypergeometric distribution is nothing new, but it's the same counting technique for without replacement, without order case. If you have any question from previous week, you may go ahead now. Okay, in case there is no question, let us move on to the next topic. And the next topic is where you are interested in number of successes per unit, not the number of successes itself. this time your variable of interest is number of successes per unit. And this is where most probably we will tell you what is the distribution of X. But even if we don't tell you, if you see a variable's description is like number of successes per unit, you should know that this has a Poisson distribution. And when you know X has a Poisson distribution, the formula sheet will tell you what is the probability mass function of Poisson, what is the mean of Poisson, and what is the variance of Poisson distribution. If you get any idea from the question that X has a Poisson distribution, you can directly go to the formula sheet to see that the probability mass function of Poisson is this one. And if you see this probability mass function and this this mean expression, if you see this probability mass function and this mean expression and the variance expression, in this function, other than lambda, other than X, there is one unknown constant, and that is called lambda. And like the other parameters of binomial hypergeometric, lambda is called the parameter of Poisson distribution. That is, when you knew X is binomial distribution, you used to look for two things in the question, N and P. These two values are called parameters of binomial distribution and they come from the question. When you knew X is hypergeometric, you looked for three things from the question, N, K, and capital N. These three are called parameters of hypergeometric distribution. Similarly, here, when you get an indication from the question that X has a Poisson distribution, the only thing you are going to be looking into the question is the parameter of Poisson distribution, and the only parameter of Poisson distribution is lambda. And what is this lambda? This lambda is the average number of successes per unit. And this will somehow be given in the question. Now I have just highlighted a word unit. This is one of the words we play around in Poisson distribution. This is one of the word where you will see the tricks in the question. And you have to make sure when you are solving a question about Poisson distribution, you identify a value of lambda from the question. The only thing you have to make sure is that the unit of lambda and the unit of X, they are same. Because sometimes we provide you a lambda in a different unit and ask you the question in a different unit. So in that case, you should convert either lambda to the same units of X or X to the same units of lambda. And I will get to that one. The general map of Poisson distribution is it is like you have an infinite population. That is broken into pieces, equal pieces. Many of them, infinite of them. And there is an event that's happening all over your population. It happened here, 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 and it's happening everywhere. In some boxes, it's happening 0 times. In some boxes, it is happening 1 time. In some boxes, it's happening 2 times, and so on. So what you are interested in is the number of successes per rectangle. That's your unit. The rectangle is your unit. So you're interested in the probability sometimes, or maybe the average sometimes, that if you pick one of these boxes randomly, you'll be interested in the number of happenings of this yellow event in that box. X will be number of dots per unit, and the unit is this box, every box, and there are infinite boxes in your population. So in the population, this event is happening many times, but in a specific box, it will happen how many times? Maybe 0 times, maybe 1 times, maybe 2 times, 3 times, 4 times, and up to what? We don't know. You may have 10 dots, may have 11 dots with no upper limit. Let us have a question. Let me copy a question from book probably. Any questions before I start, or in the meantime, I'm copying something from the book. If you have any questions, please go ahead. Yes, Muhammad Faris.
Yes, Doctor. What is the difference between number of successes and number of dots?
Number of dots is the number of successes.
So
I'm denoting every success by a dot.
yes, so lambda, it is similar to x.
Lambda is the average of x, average number of successes.
Okay.
Per square.
Okay.
I would say per rectangle. These shapes are like more like rectangles. Yes, I found a question that is nice. This is question number 3.160 in your book. And here it is. Now this question, let us read this question and mark the important information. The question says that the number of telephone calls, this is your variable, that arrive at a phone exchange is often modeled by a Poisson distribution. So X is modeled by a Poisson distribution, and this yellow highlighted thing is your X, number of telephone calls per. The unit is not mentioned yet. The unit will be mentioned in the question. Assume that on average there are 10 calls per hour. Look at this. This is very important information. There are 10 calls per hour. That's average number of calls per hour. That's lambda. So I'm going to write down these two pieces of information. I'm going to write X as number of calls per. I'll leave this space. I'll fill this one after a few minutes. And then I have one important information. Average number of calls per hour is 10. 10 calls. These are two pieces of information I have from the question. Now I'll start with part A. Part A says, what is the probability that there are exactly 5 calls in 1 hour? So the question is interested in per hour, 1 hour. So let me define X per hour also. Because the question is interested in 1 hour, I will define my X to be number of calls per hour. And where am I interested? Exactly 5 calls in 1 hour. So in part A, I am interested in X equals 1 per hour. I'm focusing a lot on the units because this is the only, not the only, but this is the major trick that you will see in the questions. Now you need the probability of X equals 1 per hour. You need the distribution of X. You need the distribution of X, and it's given that X follow a Poisson distribution, and the only parameter of Poisson distribution is given in the question. It is 10 calls per hour. Lambda is 10 per hour. Muhammad Ali.
Is it X equals 5?
Come again?
Is it X equals 5?
Oh, yes. 5 calls per hour. Yes, thank you. The question is saying 5. Yes, absolutely right. So we can write the probability mass function of X easily. Your f of X is just plug in the value lambda into the function e to the power minus lambda to the power of X divided by X factorial, where X starts from 0, 1, 2, all the way up to infinity. Because in next 1 hour, you may expect no call, 1 call, 2 calls, 3 calls, 4 calls, 5, 6, 7, 8, any number of calls. Now the question says find the probability of x equals 5. We can go ahead and solve this question. Why? Because this is very important, because the unit of question and the unit of lambda, they are same. I can only go ahead if they have the same units. So this is equal to e to the power minus 10, 10 to the power 5 over 5 factorial. Give me the answer up to 4 decimal points.
Zero point 0.0378.
0.0378. If someone can confirm, I want
Yes.
one more student. Yes, okay. So this is the probability of x equals 5 per hour, or 1 hour. This completes the solution of part A. That was the easiest part. Why? Because luckily the unit of lambda given in the question and the unit of question, they were same. So you were able to solve it quickly. Part B is also easy. What is part B? Part B says, what is the probability that there are 3 or fewer calls again in 1 hour? So this question is also 1 hour, in 1 hour. So you don't have to play around with the units of lambda in this question either. The only thing that's different in this question is that instead of x equals 5, now the required thing is 3 or fewer. So part B says probability of x fewer or equal to 3 is required. So this will be probability of x equals 0 plus x equals 1 plus x equals 2 plus x equals 3. So you can simply plug in the value 0, 1, 2, and 3 into the function, and there is no shortcut for that one. So e to the power minus 10, 10 to the power 0 over 0 factorial, e to the power minus 10, 10 to the power 1 over 1 factorial, e to the power minus 10, 10 square over 2 factorial, e to the power minus 10, 10 cube over 3 factorial. And this will be the answer. 3 or fewer calls. Yes, this is the answer. Now comes the important part. See, what is the probability that there are 15 calls in next 2 hours? Now look at the question. There are exactly 15 calls in 2 hours. Now the question is x equals 15, but the unit is not per hour. The unit is 2 hours. I'm going to write this question here. Probability of x equals 15 per 2 hours. This is required. You have the distribution of x per hour. You don't have the distribution of x per 2 hour. But the good thing is, if x has a Poisson distribution with lambda equals to 10 per hour, per 2 hour will also be Poisson. The only thing you need to adjust is the value of lambda. So if your lambda was 10 per hour, you expect 10 calls on average, 10 calls in 1 hour. How many calls do you expect in 2 hours? 20. 20, of course. So your lambda for this question will be 20 per 2 hours. And your f of x for this question will be e to the power minus 2 times 10, 2 times 10 whole to the power of x over x factorial, where x is 0, 1, 2, all the way up to infinity. So you replaced lambda by 2 times lambda. Omar Adnan.
Yes, doctor. Can I convert x to be per 1 hour?
You can also do that.
But x will be 7.5. And
yes.
How can I get the factorial of it?
That's the problem. That's the problem in converting x. That is the problem in converting x. So in some questions, yes, you can, but if that is the problem and you are getting a decimal for a discrete variable, then you have to go the other way.
Oh, so for this question, I cannot.
You cannot, yes.
Yes, thank you.
So what I do for this question is I directly find the probability of x equals 15 by simply plugging in e to the power minus 20, 20 to the power 15 over 15 factorial. And this will be the answer of this this part C. Let us go on to part D. What is the probability that there are exactly 5 calls in 30 minutes? Again, the unit, the basic unit that was given in the question was per hour. But the question is saying exactly 5 calls in next 30 minutes. If you are expecting 10 calls in 1 hour, how many calls are you expecting in 30 minutes?
Five.
Half of 10, 5, absolutely right. Probability of x equals 5 per 30 minutes. This is required. Again, you need lambda. You need lambda per 30 minutes. So here your f of x will be e to the power minus half of 10 whole to the power of x divided by x factorial. Where x is again from 0, 1, 2, all the way up to infinity. So here the question says probability of x equals 5. You just plug in 5 e to the power minus 5, 5 to the power of 5 over 5 factorial. Now this is confusing because there is 5 everywhere. Let me write this one as 10 over 2 so that you know where is x and where is lambda. Lambda is basically 10 over 2. This should give you the answer for part D. So to convert lambda into the right unit, you may scale up the lambda or scale down the lambda. In part C, I scaled up the lambda. I multiplied it by 2 because the question was asking per 2 hours. In part D, I scaled down the lambda. The question was asking for per 30 minutes. Part C or part D, Ahmed? Okay, thank you. Muhammad Ali.
Doctor?
Yes. Yes, Muhammad Ali.
Will every question indicate that the question is modeled as Python or not?
Yes, this question is indicating, but even if it was not indicating, whenever you see a question of number of successes per unit, it's Python. Number of successes per unit. Number of happening of any event per unit.
Okay, thank you.
Muhammad Faris.
Dr. Bart, C 5 zeros, not 4.
5 zeros.
Sorry for that.
5 zeros. Any question? There is one tricky thing that may happen. What if I ask you a question in part E? Find the probability of having at least four calls in next 30 minutes. Now there are a few tricks in this question. One trick is about the unit. We have already played with this unit in the previous question. The unit is 30 minutes. So one trick is to identify the lambda per 30 minutes. So the first thing you need to know is that P of x equals x is e to the power minus 1 over 2 times 10, 1 over 2 times 10 to the power of x over x factorial, where x is 0, 1, 2, all the way up to infinity. The second thing is, and the main trick that I want to explain in this part is, what is required? The required thing is probability of x at least 4. At least means greater than or equal to. Can you find this probability? Abdul Aziz.
We can find the negation of this probability and then subtract it from 1.
Yes, you're absolutely right. We cannot find this probability directly because there is no upper bound of Poisson distribution. This is basically equal to probability of x equals 4 equal plus 5 plus 6 plus 7 plus 8 plus 9 up to what we don't know there, because there is no upper bound of Poisson distribution. So here you don't have a choice. You have to use the complement rule. So you can only find it through this way, equals 1 minus probability of x less than 4. And when you are dealing with a discrete random variable, be careful with the equal sign. If equal sign is there on the left side, don't put it on the right side. If it is not there on the left side, put it on the right side. So because it was greater than or equal to 4, the complement is less than 4. And this I can find 1 minus probability of x equals 0 plus probability of x equals 1 plus probability of x equals 2 plus probability of x equals 3. So there are some questions of Poisson distribution where you are bound to use the complement rule. This you can find easily, like 1 minus e to the power minus 5 to the power 0 over 0 factorial, e to the power minus 5 to the power 1 over 1 factorial, So who can tell us the answer? Poisson distribution. X is less than or equal to 3. The mean is 5. So it is 1 minus 0.265, which is 735. Let me know if I'm right. Anyone who did the calculations, let me know that this is the right answer. .735.
Yes, it is correct.
What if I ask you in part F, find the standard deviation of number of calls per in next 2 hours? What am I asking you to find? Number one, look at the variable of interest. Your variable of interest is number of calls in next 2 hours. So for this X, your probability mass function is this. That is e to the power 2 times 10 . And what's required in this question is what? Find the standard deviation of this one. So what is the standard deviation of Poisson distribution? Let's go back to the formula sheet. And where is it? We look here. What is the standard deviation? The standard deviation of X will be the square root of variance, which is the square root of lambda. So you're able to identify the lambda from the question, just take the square root of it. Take the square root of 8, that will be the standard deviation. So lambda here is 20. So the standard deviation sigma of X will be the square root of 20. That will be square root of 20. 4.4721. Calls or call square. What will be the unit of this sigma? The unit of X is calls. 0 call, 1 call, 2 calls, 3 calls. What will be the unit of sigma?
Calls.
Same calls. What will be the unit of sigma square? Variance.
Call square.
Call square. Any question from the Poisson distribution? This is Poisson distribution. Now let's go back to the formula sheet. What will be given to you in the formula sheet? For you, the general formula of Poisson distribution will be given. This will be given. E to the power minus lambda t to the power x over x factorial. I think this will be given. Let me check the formula sheet. Is it? Anyone who saw the formula sheet of midterm exam?
Yes.
It's in terms of lambda t. Yes, this is what is going to be given. 0, 1, 2, all the way. And the mean is lambda t. And the variance is lambda t also. So lambda t means t is there for the adjustment in units. Most of the times t is 1, but in some questions t is other than 1. Maybe more than 1, maybe less than 1, depending upon whether you are scaling up the units or scaling down the units. Like when you convert it from per hour to per 2 hour, t was 2. When you convert it from per hour to per 30 minutes, t was 1/2. So it depends whether you're scaling up or scaling down.
T, what does it represent?
T represents the change in units. It represents the ratio of original lambda to the converted lambda.
So in the previous question, it was T1?
In part A, T was 1. Where is it? In part A, T was 1. You used 1 times 10 here.
Yes.
1 times 10, 1 times 10. In part B, T was again 1. In part C, T was 2. See, I wrote 2 times 10.
Oh, yeah, I understand now. Okay, thank you.
In D, I wrote T 1/2. That is why I was not writing it -5. I was writing it 10/2.
Yes.
Muhammad Shafiq.
Doctor, is there anything we have to memorize in chapter 3?
Chapter 3, you have to memorize. I don't think you have to memorize anything. Not even chapter 2. Do you have to memorize something in chapter 2?
I don't think so.
There's nothing you have to memorize. All the things that are not given in the formula sheet, they are logical things. They are not there to memorize. We did not give you those things in the formula sheet because they are logical. They are elementary school level. I'll give you an example. Not even probability. A union B whole complement is A complement intersection B complement. This is not given in the formula sheet, but this is the school level thing. This is something very, very basic. So things like this, they are not given. But other than these things, whatever is new in this course, they are all given in the formula sheet. Any other questions? Okay, now we come to the most difficult distribution of this chapter, which is the negative binomial distribution. And I will try to create a connection between binomial and negative binomial distribution. And for this one, I need to summarize what we did in binomial distribution. Now, what we did in binomial distribution was as follows. Whether with replacement or without replacement, whatever, I'm not going into that discussion. What we did was we were interested in a variable x that was number of successes. You were interested in how many successes in next n trials. You knew that you were going to perform the experiment 10 times, 20 times, 30 times, whatever number of times, n was known. And you were interested out of these 10 trials, how many of them will result in success, how many of them will result in failure. This is where you were interested. And for each of these 10 trials, you were looking for these 4 properties. What 4 properties? Number 1, 2 possible outcomes. success or failure. Number 2, fixed probability of success. Denoted by P. Number 3, independent trials. Number 4, experiment repeated. Fixed number of times, n times. Now here I'm going to mark 2 important things. The experiment is repeated n times. In advance, you know the experiment is going to be repeated 7 times, 10 times, 20 times, 30 times, and the interest is in number of successes. This is where the difference is going to be in binomial and negative binomial. The remaining things will be same. I'll give you a question for binomial. Let me copy some of the questions that we already took there and create a negative binomial question out of those. Flip a coin 10 times and X denotes the number of heads. Let us go with this, or let's go with a more practical example. Of all the patients suffering from a particular illness, 35%, next 100 patients, X denotes the number of patients who experience the improvement. Let me copy this. And paste it here. And can anyone tell me how to crop it? Crop. How do we crop it? Draw. Crop. No. Picture. Order. There is no way of cropping.
We need number 5.
I need one of these two, maybe number 7. I need only number 7.
Yes, try cut. Maybe it works.
Cut will take
all
of it. Let me copy it again from the book. I think this was from the book. I will copy only number 7 from the book.
I think next to the cursor, below draw, that you might cut from that, like crop. No, draw, go up.
Draw.
Up below it, and then left. That might be it.
Lasso select. No, this is not working. Nothing. Let me
go to picture.
Go to picture. Okay.
The last item. Here, home, insert, draw, view, class note, picture.
Picture.
Yes, maybe no picture from the bar, above bar.
From above the bar.
Class
Where is
note,
it?
Class note, book.
Class notebook.
Yes, picture.
Where is picture?
No. Next to class notebook.
Okay, we have picture.
Yes, maybe you have here some options. Like word office. No options here.
No options here, but
Yes.
I can go back to the book and I can copy only this part. Okay, here I am with example number 7. In this example, I'm going to point out everything that we just wrote about, the 4 properties and the definition of X. And then I will flip the 2 of them. Here, you are interested in what? You're interested in X, which is number of patients with improvement. I'll call this thing as success. This whole thing, I'll call it as success. This whole thing. And for this experiment, every trial had 2 possible outcomes, success or failure. For every patient, the probability of success was 0.35. The probability of experiencing any improvement is 0.35. Patients are independent, trials are independent. How many patients do you have to see? We already know we have to see 100 times. And there it is, 100 patients. There is 35%. So all in all, for this whole information, we said X follows a binomial distribution with n equals 100 and p equals 0.35. And we can find any corresponding probability from this one. But what if I switch X and N? What if I switch X and N becomes variable and X becomes fixed? What if I ask you the question that of all the patients suffering from a particular illness, 35% they experience improvement. What if I tell you that I'm going to start selecting patients one by one? For each patient, I will check if he's experiencing improvement or not. And I will keep checking patients until I have 10 patients who experience the improvement. So I want 10 successes. And I will keep selecting until I get 10 successes. In that case, I don't know how many times do I have to perform the experiment. My number of times I perform the experiment has become the variable now. I may have to select 10 patients, maybe 11, maybe 12, maybe 100, maybe 200 patients until I get 10 successes. Same is true for flipping the coin. In binomial, you were flipping the coin 10 times and you were interested in how many heads do you get. Now I'm flipping the question and I'm saying you will keep flipping the coin until you get 6 heads. So how many times you have to flip the coin? Maybe 6 times, you get straight 6 heads. Maybe 7 times, maybe 10 times, maybe 20 times, maybe 100 times, maybe 200 times. So if I flip the definitions of N and X, the random variable N becomes negative binomial in that case. And I'm not going to use the notation N, I'm going to use the notation X for the variable again. So now I'm going to write the definition here that if your X is the number of trials, not the number of successes. Until R successes. All the properties, remaining properties are same. 2 possible outcomes. P is constant. Trials are independent. An experiment is repeated until we get R successes. So you see, I flipped the definitions of property number 4 and the variable itself. Previously, I knew the number of trials. I was interested in number of successes out of that n trials. Now I know I need that many successes and I'm interested in number of trials basically. So I just flipped the definition of X and N. In that case, now this new X will be negative binomially distributed. And negative binomial distribution has two properties, two parameters, n and no, sorry, not n. There is no n in this one, R and P. And if you know that X has a binomial distribution, the mass function of X is X minus 1 combination R minus 1, P to the power R, 1 minus P to the power X minus R, where X starts from what? If you need 7 successes, how many trials do you need to get 7 successes? What should be the minimum value of X to get 7 successes? How many trials do you need? What do you think?
7.
You need at least 7. So the domain starts from R and then R plus 1, then R plus 2 and all the way up to infinity. You may need infinite number of trials. And if you're able to recognize that X has a negative binomial distribution, the expected value will be given as R over P in the formula sheet, and the variance will be given as R into 1 minus P over P square. And we will do some examples of this negative binomial distribution in the next class, where you will be interested in number of trials until R successes. Not the number of successes out of n trials, number of trials until R successes. So tomorrow, inshallah, we will try to finish chapter 3 and we'll do some examples of chapter 3 also. And then the day after tomorrow, we'll start chapter 4. If you have any question from chapter 3, you may go ahead now. We are almost done with chapter 3. And if you don't have a question, you can leave the session at this point.
Thank you, Doctor.
Welcome.
Thank you.
Doctor, I have a request.
Yes,
Okay.
Please go ahead.
Could you please next homework make it multiple submissions if it's okay?
Multiple submissions. What is the problem in single submission?
Because sometimes mistakes happen.
If that happens, you send your instructor, whoever is your instructor. In your case, it's me. So you send the correct solution to your instructor, or just make a request to your instructor. He will give you the second attempt, but that should be within the deadline. OK.
Oh, okay. Even it's like a long process, but it's okay.
No, just send an email that I want a second attempt. So I will immediately give you.
Okay.
But because the deadline is 2nd of July? So it should be within 2nd of July.
Of course.
Yes.